Okay, so let's pick up where we left off last time and kind of look at the sum total of all the data now that everybody's filled it in. Although some people are going to get yelled at, like Mr. Barnett. Where's your third time?
Oh, I did it at 35. It was 155 seconds.
155?
Yeah,
You sure?
yeah. Sorry about that.
Uh-huh. Okay. Yeah, what about Mr. Song? Hmm. Yeah. Or let's really yell at Mr. Miller, it looks like. Death. I'm going to waterboard you guys. Um, all right. So anyway, uh, or Eugene. You know what, Eugene? No chicken tenders for you today. Yeah. Okay. No chicken tenders. All right. So what do we notice about the results of this? Well, obviously, it took longer. The more suits, and hence the more cards you had to sort. So what I did was I actually changed a little bit of what I computed down here at the bottom. I computed for each of the sets of numbers. Okay, so for all of the one suit sorting, so that's three columns worth, I computed the minimum time that it took anybody. In this case, it took across you guys and the other class 13.04 seconds was the least amount of time anybody could do one suit in. The average was, and again, this is across all trials, all classes, 20 and a quarter, and the maximum was 53. Okay, so let's think about why might there be some variance here, and why might the averages be so far off of the min and the max? Okay, yeah, how well or not well it was shuffled. So it could have been the case that maybe you ended up with all of the cards already being in order when you shuffled them, right? That could theoretically happen. Not likely, but it could theoretically happen. In which case, if they're mostly in order when you start, it doesn't take you as much work to sort them because, well, it's already done. What about the max?
Complete worst order from there.
Right. It could be. And what would the complete worst ordering be? Does actually kind of beg a question. Um, well, it depends on how you sorted them. First off, the actual like process that you used. We'll talk about that more in a little bit. But yeah, like maybe they were really, really, really well sorted or well shuffled, and you just got unlucky. Okay. It's also possible that uh, well, just looking at some of the numbers, I mean, and actually, Mr. Inshow, you're the one who had the 53 seconds. So, um, yeah. So I don't know. Maybe like his phone buzzed because he was getting a bunch of upvotes on a Yik Yak post where he was, complaining about the CS professors at this college, or what Sparks does to your digestive system, or whatever else, right? And he got distracted and forgot to stop the timer or take out the amount of time, right? Do something like that, right? So it could be that there's some um, uh, human error in this data set because, of course, every one of these times was recorded by you guys doing it, not a computer. Okay. Okay. So we see sort of similar things with the uh, hold on. Oh no, no, I'm sorry. I was misreading this. Similar things with the other suits. So for two suits, the minimum was 22, the average was just shy of 50, maximum 84, and so on. Okay. So and the reason that I put in min, max, and average is because, of course, that's what we sort of care about with algorithm analysis. That yeah, maybe sometimes you get lucky, but there is going to be some sort of theoretical minimum. There's also a theoretical maximum, And then in practice, you're going to be, well, somewhere in between the two. All right, so I just copied those numbers up here. And then for sake of making the graph better, and I actually didn't do this with the morning class, but Dr. Brown, when he was looking at this over my shoulder, says you should put 0 in as one of the data points, because obviously, if we had no cards to sort, how long should that take? 0 seconds, okay? So, like, mathematically, we don't need that there, but it does make the graph a little easier to see, as we'll look at. Okay, so what I graphed here were in blue, I've got the minimum, in red, I've got the averages, and in yellow, I've got the maximum numbers. And you'll notice that the maximum numbers are a little janky, but the minimum and the average, well, first off, is it clear that it's not a straight line that would go through all of them? Okay. But that does beg the question then, if it's not a straight line, what curve would be a good curve to fit to this data? Well, just looking at it, what does it look like might seem reasonable? If it's not linear, what else could it be? It could be exponential. Okay, and when you say exponential, what do you mean? Like, give me an example of an exponential function. No, like, give me an actual formula of an exponential function. Well, how would you write it down? Huh? What? To the power of 2. Okay, so x squared, that's not actually an exponential. Okay, exponentials would be things like 2 to the x. So there's a mathematical difference between those. But a polynomial would work. So a quadratic, for example. And just looking at it, do those look roughly quadratic? Does that seem reasonable? Yeah. Okay. They could be exponential. I mean, they could be cubic or something. But I know actually, and for reasons that we'll sort of explore today and Friday, that it is in fact a quadratic fit. Okay, so what I had Google Sheets do here, you can see next to each line there's kind of a fainter color version, the trend lines, and I've graphed those for each of the 3 cases. So the blue trend line for the mins, the red one for the averages, and then the yellow one for the max. Of course, the yellow one's a little janky, but okay. Um, and those are all quadratic curves. Now, for the blue one and the red one, would you agree that they fit pretty dang well? Okay. How could I measure, in some sense, how good the fit is? Well, how many of you guys are, say, the non-freshmen in the room, are social science majors? So, say, poli-sci, econ, right? Which one? PPE. Okay. If you haven't done a curve fit in one of your classes yet, you need to ask for your money back, right? But how do you measure how well a curve fits a given amount of data, right? The R squared value. Is this ringing a bell to those of you in the sciences and social sciences? Maybe. Is anything ringing your bell right now? Yeah, I would hope so, because that's kind of important. Okay. All right. So the R squared value is sort of a measure as to how well the curve fits the data. And what is a quote good R squared value? Well, okay, they range from 0 to 1. As a percentage, what would you expect to be a quote good fit? The closer to 1, the better. Yes, okay. But sort of where's the threshold where we're really happy if our R squared values get above what? Yeah. Yeah, 0.95. Okay, so 95% confidence, right? That's sort of it's not a perfect threshold, right? But 95% confidence or an R squared value of 0.95 is sort of, okay, that's what you would hope to get. Okay. Um, and Now, obviously, the higher the better, right? But in depending on the experiment or the data collection you're doing, there may be uncertainty, there may be noise, there may be sampling problems, right? 95% is not the gold standard, but it's sort of a good rough point there. All right, what do we notice about our R squared values for all of these? Well, the max case, the yellow one, its R squared value is 0.956. Okay, so kind of right at that threshold. But I think you guys would agree that there's some janky business going on there. Okay, but what about for the min and the average? Those are 0.99, blah, 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 right? That's really damn good. Okay, and furthermore, these averages, that's the one that I'll maybe concentrate on for right this instant, right? The averages, that's averaged over every single trial by all 46 of you guys, right? So if there's going to be variance in the data, because, well, you guys are all different people, when we average it over the entirety of all 46 of you, we should expect that any of this weird noise, like, for example, Mr. Inshill being a slowpoke, would kind of get washed out. Yeah? I'm going to pick on you for the rest of the day. And still no chicken tenders, right? Going to go to Sparks and say, nope, he's persona non grata. Yes.
With that wash out though, I mean, if someone was like disproportionately slower than everybody else, it's probably hard, or it's much harder to be that kind of proportionally faster on the other side of it.
Yes, okay, fair. But if only one person is really slow or really fast, averaged against 45 other people, any the impact of any one individual is much less is reduced when we're looking at the averages compared to the maxes and the mins, right? Um, okay. The other thing, right, with the max and the min is, as we said, you could have gotten really lucky or really unlucky. And then one other observation about the sort of weirdness going on here between uh, 2 and 3 suits. What changed there when we did this? Yeah, suddenly you had two of the same color. Okay. And maybe what that means is that the complexity actually was more than just going from 2 to 3 suits. That, the color plays an influence here that we're not measuring in some way. Okay. So it's not perfect, right? Science is messy if you guys haven't figured that out already. Um, but we get the idea, right? So what I want to convince you guys in a very mathematically precise way, though, is why quadratic actually makes complete sense here. Okay, good. All right, so for my next trick, let's go over to the webcam. And let me blow this up so that you can see it better. All right, so I've got here some of the cards, okay? And just for the sake of demonstration, let me get out, say, 4, oh, there they are, 3, 2, 6, and 7. Okay, so I'll just use 6 cards for sake of demonstration. All right, and I'm going to shuffle them. And it doesn't have to be a great shuffle, just something, okay? And let's lay them out. Okay, now, when you guys did this, how many of you actually laid out all of the cards on the table before you actually did any sorting? Okay, so you laid out all of them in a row. Then what did you do? Huh? Okay, so you started a timer, then what?
With just one
Mhm.
suit,
Let's just say one suit, yeah. Because obviously it's a lot harder to fit 52 cards kind of in a line, but just theoretically imagine that you could. Okay.
if I like to find the 2 at first, I would put that automatically less than if I found the 8 since I put it automatically, right?
Mm-hmm.
But if not, like I didn't see it, I'll put the card at first to like spot like the spin.
Okay, right. So you kind of maybe move them thinking, all right, well, if I've got about this table width, I know that the low cards are going to be kind of over here at one end, and the high cards are going to be at that end, and I'll kind of just visually estimate the continuum in between and say, okay, if I've got like a 8, that's sort of in the middle somewhere, so I'll put it roughly in the middle, and then as I put down more cards, kind of maybe keep going with it. Okay, anybody do it sort of similar to that? It's less practical to do that when you've got more cards, but yeah, okay. What about the following? Did anybody do it this way, which is you've got the entire thing either as a stack or all laid out, it actually doesn't matter, and you first searched through until you could find the 2, and then you put it in a pile. And then you searched through what was left to find the 3 and put it in the pile, and then the 4, and then the 5, and so on. Okay, did anybody do it that way? Yes. Okay, so that is actually, you changed the problem from a sorting problem to a searching problem, right? And in the morning class, we called this the Sparkle sort after Ethan Sparks. Okay, and those of you who are on football can please make sure you call him that for the rest of his existence, because yeah. Um, so okay, when I was talking with Dr. Brown having coffee an hour ago, he called that the stupid sort. Okay, which, why is it stupid? Well, it's sort of maximally inefficient. Okay, and but it's really easy to explain, and it'll be really easy for us to do the mathematical analysis of that particular method. Okay, so let's assume that we go with the Sparkle sort. Okay, so how would I do this? I've got a stack of cards here, and I would say, all right, I'm going to look at the first card. Is it the 2? No. All right, I'm going to look at the second card. Is it the 2? Yes. All right, I'm going to look at what's left. The first card, is it the 2? No. Is this the 2? Or sorry, the 3. Is the 4 the 3? No. Is the 5 the 3? No. Is this the 3? Yes. Okay, so move it. All right, look at what's left. Is this the 4? Yes. Is this the 5? Yes. Is this the 6? Okay. And so in this case, I got lucky in some sense that they were kind of already mostly in order, and that's just because of sort of the shuffling. Like, that's just the shuffle I got, right? Whatever. Yes? Okay, good. So let's think about that algorithm then. If we do it not really by sorting anything, but just by searching and going through them in order, then would you guys agree that the best possible situation that we could have is when there happen to already be sorted? Yes? Okay. How many operations does it take to do that if they just so happen to be already sorted? And here there's 6 cards, so how many operations does it take? In some sense, it still takes 6 because I still have to look at the 2 and say, hey, is this the 2? Right? So the act of me making a decision or examining the card to see if it's a 2 or not still requires effort. Yes? Okay, so if there are 6 cards, at minimum, how many steps or so do you think it takes? 6, right? That makes sense, right? Because I still have to look at each card to make sure that it's the correct thing. Okay, good. All right, what would be the absolute worst nightmare for these cards to be laid out as? Yeah, okay. Which, by the way, there's no reason that we have to start on the left when we're doing this, but just for sake of demonstration, I will. So this is in some sense the worst possible ordering that you could end up with for that algorithm. Okay, because what I have to do is I first want to find the 2. How many cards do I have to look at before I find the 2? 6. Okay. Then with what's left, how many cards do I need to look at to find the 3? 5, then 4, then 3, then 2, then 1, right? Because obviously once there's only one card left, there's only one thing to look at. Okay, so does that make sense? Yes? Okay, so let's go over to the iPad. Oops. Okay, let me get these out of the way and switch. Okay, so let's sort of do the counting here for the best of times and the worst of times. You see what I did there, right? Yeah? It was the best of times, it was the worst of times. What's that from? Charles Dickens. English major. It was the best of times, it was the worst of times. What's that from? I already said it was Dickens. Mm-mm. Melville wrote Moby Dick, not Dickens. Mm-hmm. It's a tale of two cities. Yeah. Now, what's a good line from Moby Dick? Or anyway, does anybody actually know the first line of Moby Dick? No? Call me Ishmael. You guys don't read, do you? Ah, kids these days. All right. And it's really too bad because there are even computer science terms that come from classic literature. For example, this word, Indian, that comes from Gulliver's Travels. And we use it to describe, like when we write bits, which end has the high bit and which end has the low bit. Well, it's either big or little Indian, and that's a funny joke from Gulliver's Travels. But none of you would get that because you haven't read any dang kids these days. All right, so the best case scenario, the cards happen to be sorted. And if we had 6 cards, it took 6 operations. Okay, so in cards would take in operations. Right? I could give you 1,000 cards. Like, imagine I found some printer to make me these things that just forget the suits and clubs and all of that, just had numbers 1 through 1,000 on them. Yeah. Um, I could have, like, if we had those, then we could have done it with those instead of with the playing cards. Turns out it's easier to get the playing cards on Amazon. Um, okay, but what about the worst case? Let me call this anti-sorted. So they're sorted, they're just in backwards order from what we want. Okay. All right. So with the 6 cards that were backwards sorted, how many operations did it take to get the 2 dealt with? 6. How many did it take for the 3? 5, and then 4, and then, and then, and that equals, okay. How did you add up those numbers? Ah, so what did you type? You did 6 plus 5 plus 4 plus 3 plus 2? Okay, so no offense, Liam, but that's the stupid way to do it. And I'll explain the smart way to do it a little bit later. Okay, so it took 21 operations. Okay, sort of at most. Well, we need to generalize this. This was just for 6 cards. What about if I had n cards? How many steps would it have taken to find the 2 if they were sorted in reverse order? And there are n cards. N times. How many would have taken for the 3? N minus 1 and n minus 2. Let me go ahead and write that one explicitly. All right, it would have taken that many. All right, smartass, what does that add up to? No, what does n plus n minus 1 times plus n minus 2 plus dot 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 plus 3 plus 2 plus 1 add up to? Huh? No, that'd be if they were multiplied. This is added, so it's not factorial. Okay, good idea, but it's not that. Okay, you mean to tell me that you're going to add up a whole bunch of positive numbers and get a negative answer? Huh? Okay, so what does that mean then? I'm sorting 0 cards? Well, and we're in the worst of times, right? We're assuming from the get go that they're um, anti-sorted. Okay, just for sake of analysis. Okay, so your calculator ain't going to help anymore, will it? All right. Well, this is where you have to use your damn heads, gentlemen. Okay. So earlier I asked Liam, or Liam asked himself, what's 6 plus all the way down to 1, right? And you used your calculator. So you did 6 plus 5 plus 4 plus 3 plus 2 plus 1, right? Okay. I'm going to change the problem. I want you to add the numbers from 1 to 100. 1 plus 2 plus 3 plus 4 plus dot 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 plus all the way up to 100. Or you can start at 100 and work your way down. Okay? What's the stupid way of doing that? To do what Liam just did with 6 plus 5 plus 4 and so on. Okay? Let me show you the smart way to do this. Okay, well, what I notice is that 101 add up to 101, and 99 and 2 add up to 101, and 98 and 3 add up to 101, and I had 100 numbers, so I put them into 50 pairs, and so I have 50 pairs, each of which is 101, and so the answer is 50-50. Done. Okay, how many cranial explosions just took place? Yeah? That's thinking with portals. No. Okay, you guys, surely to God, you get that reference. At least one of you in this room has to get that reference. Xander, would you please elucidate everybody else? It's from the game called Portal. How many of you have played that game besides Xander? Okay, so have you guys seen the South Park episode where Eric Cartman becomes the substitute calculus teacher, and it's making fun of the movie Stand and Deliver? How many of you guys watched that in high school? It's about a actually pretty famous teacher named Jaime Escalante, and he went into a school in Los Angeles that was like, really on the last leg, and started teaching a calculus class, and got a whole bunch of students to do well on the AP exam. So well, in fact, that the College Board thought that they all cheated and made them redo it while they all stood there and watched them. And he's like, yeah, you wouldn't have done this if this was Beverly Hills High School, would you have, huh? Right. Okay. Every calculus class in high school has to watch this movie. Well, there's a South Park episode where they're making fun of it, and Cartman becomes this teacher, and he comes in and he says, "I am Eric Cartmanez, and I'm here to teach you calculus." And he's got like this really crappy comb over or whatever. But anytime something goes wrong, he's like, "How do I reach these kids?" Right? And he really exaggerates it. How do I reach you kids? Chicken tenders? Okay. Well, okay, so let me go with the opposite approach, which is I'm going to deny you chicken tenders unless you get reached. No? Okay. So, what was the trick here? The trick here was to realize that actually just adding them all up was going to be inefficient. It works, but it's not smart, right? but noticing that I can pair up the first and the last and so on. And if I've got a bunch of numbers and I pair them up, how many pairs do I have? Well, half as many, right? So if I have here, let's go back to our problem. What does each pair add up to? N plus 1. And how many pairs do I have? I have n over 2 of them. Because if I have n cards, well, and I'm pairing them up, I have half as many of those pairs. Okay, now some of you may recognize it if I write it in this form. Well, maybe if I could write in Greek today, that'd be great. Yes? All right, so what is this big, scary sigma looking thing? And I would hope that you all recognize this symbol, right? Because we have fraternities that have that in their thing, like Kappa Sigma, for example. Yes? Okay, so what does this mean? It means start with I equals 1, take the formula I, add that to a running total, and keep going, incrementing I each time until you hit n. So this means, this is shorthand for writing 1 plus 2 plus 3 plus 4 plus 5 plus dot 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 all the way up to n. And what we just observed is if we pair kind of from the outside in, then we have pairs of n plus 1 and n over 2 such pairs. Uh, Furthermore, I claim that this is always an integer, a whole number. Why do I know it's always a whole number? Well, first off, what am I adding? I'm adding up a bunch of whole numbers, right? Can I possibly get a non-whole number as the answer if I'm adding together a bunch of whole numbers? Liam? Okay, so let's go to that in just a minute. I know that the answer has to be a whole number because I'm adding up a bunch of whole numbers, yes? All right, this formula, is it always a whole number? Well, there's a division by 2, so you might look at that and say, wait a minute. Well, suppose n is odd. Well, if n is odd, then what is true about n plus 1? And being even means you can divide it by 2 evenly, hence the name, right? So regardless of whether or not n is odd or even, one of those two numbers, n or n plus 1, is an even number. And that means it's divisible by 2. And then you multiply by the other thing and you get whatever. So, yes. A middle function?
Yeah, the fact that they're paired up together, if you have like 15 operations, what's the
Okay, so in that case, you can think of it as um, you can think about it as having like, so if you had an odd number, right, you still pair them, the one in the middle, you pair it with itself, and then just sort of subtract that back out at the end. Um, but yeah, it turns out it's the same formula, right? It's not that hard to see. Okay, how many of you guys saw that in high school? That formula, right? The sum of the consecutive integers. No, didn't see it in high school. Yeah, well, you went to high school in Texas, didn't you? Yeah. So we'll blame it on the Texans. Okay. Okay. Well, um, I've got this formula n times n plus 1 over 2, and I could, of course, write that as that, right? And I'm going to, and I'll make this precise later, what I mean here. I'm going to say that this is basically just n squared. Okay. Um, why can I sort of disappear the n over 2 and sort of concentrate on the n squared over 2? Well, for very large values of n, which is essentially the question we'll be asking, is what's the long-term behavior of these algorithms? Who matters more, n squared or n? Very much n squared. Okay, a way to illustrate that would be, let's suppose that you're walking from here to Sparks for your chicken tenders, except Eugene, because he doesn't get any chicken tenders today. And you find, you happen to see a $100 bill laying there on the ground. What would you all do? You would take it, right? And you'd probably be pretty happy that you just found a Benjamin laying around on the ground. That's awesome. What would you do with that $100? Or do I not want to know? Okay, well, that's a reasonable thing to do. But like maybe you could like order a bunch of pizza this weekend, or you could buy in all of you and a bunch of your buddies to go to whatever party's going on this weekend or something, right? But you'd be pretty happy to have $100 extra that you didn't have when you walked into class today. Yeah. Okay, if I walk over to lunch to get my chicken tenders and I pick up that $100 bill, am I going to be happy? Am I going to be as happy as you guys are? Probably. But like, does $100 make a material difference in my life? Less so than it does in yours, okay? Because I have a job and stuff. Well, if Bill Gates walks over to get chicken tenders, okay, then does that $100 have any material impact on his life? In fact, he would lose money to stop whatever he was doing and pick it up in some sense, right? And even if he did pick it up, he'd probably give it to one of us because he's the real MVP. Well, along with the huh? Well, okay, yeah. Um, I don't know. I have to say though, after my cell phone reception is I don't even have a 5G capable phone, and I get 5G service now. Thank you, Bill Gates and COVID vaccines. Yeah, no, yeah, good. Okay. Um, okay. So there's a sense, and what we'll do kind of the remainder of today, but especially on Friday, is to make clear what I mean when I say squiggle in squared. Like that has a technical, I'm not just pulling this out of thin air kind of mathematical meaning. That's what we want to kind of suss out is what that means. Okay. All right. Now, that was one algorithm that we could have done, which would be changing the sorting problem into a searching problem. Okay. But there are other ways that we could do the sorting. And so for that, let's go back to the cards, and let me show you another technique for sorting that maybe some of you guys use. Okay, so let me shuffle them again, and hopefully that my shuffle doesn't suck too bad. And let's see what we get: 6, 3, 5, 4, 7, 2. Actually, this isn't too bad for demonstration's sake. Okay, so the technique I'm going to show you is what's called the bubble sort. It's the easiest sort or an easy method to explain. It's not particularly efficient computationally, but like I said, it's easy to explain. Okay, so what I'm going to do is I'm going to always work pairwise. I'm going to start with the first pair of cards. I'm going to say, are these cards in the correct order? Just those two. And we would say, no, they're not, because 6 should be to the right of 3, not to the left of 3. So what am I going to do if they're not in the correct order? I'm going to swap them. Okay? And then I'm going to move on to the second pair. And I'm going to say, are these in the correct order? No, so I'm going to swap them. And then I'm going to say, are these in the correct order? No, so I'm going to swap them. Then this pair, are they in the correct order? Yes. So I move on to the next pair. Are these in the correct order? No, so I'm going to swap them. Okay, so this method is called the bubble sort because what is the result? The highest card sort of bubbles its way to the right, and the smaller cards are going to bubble their way to the left. But after one pass through, what am I guaranteed to have in the final spot? The 7, the biggest card, he bubbled all the way to the right. Okay, so can I repeat this procedure? But do I need to do anything with this last card anymore? Excuse me. No, because I already know he's in its sorted position. Okay, so I just did the problem with 6 cards, but now I only have to deal with 5. Okay, and I go back through it. 3 and 5, are they in the correct order? Yes. 4 and 5, are they in the correct order? No. Switch. 5 and 6, are they in the correct order? Yes. 6 and 2? No. Okay, and so now what's true about those two? They're in the correct order and they're at the correct end. And how many cards remaining do I have to deal with? Just 4. Repeat. 3 and 4, correct order? Yes. 4 and 5, correct order? Yes. 5 and 2, correct order? No. Swap, and the 5 is now in its final spot. 3 and 4, correct order? 4 and 2, correct order? No. But now the 4 is in its correct spot. 2 and 3, correct order? No. Switch. 3 is in the correct spot, and of course, since we only have 1 card left, by default, it has to go there. Okay, so this algorithm, did anybody actually do it that way when you were sorting the cards? Okay, probably not, and that's fine, right? I didn't want to specify the card sorting algorithm. I could have, right? But for the sake of demonstration, I wanted to just, you just sorted them, right? It didn't specify exactly how you went about doing so. That, by the way, is another explanation for the variance that we saw in our data, is the fact that you guys probably all sorted them in lots of different methods, right? If I had said from the get-go, thou shalt sort in this method, we would probably have a little bit cleaner data, because we would have all been using the same method. Okay, now, what we're going to do is to sort of analyze this method of sorting, okay, in a more, well, A, mathematical, but B, taking this to the limit, okay. Here I only did this with 6 cards. And the only reason I did it only with the 6 is just to explain what the heck the algorithm is, okay. What kind of operations did I have to do in this algorithm? What kind of steps were required? Okay, so there was a decision. For each pair that I looked at, I had to say, is the left one, quote, less than the right one, right? Meaning, are they in the correct order? Okay, so there was a decision that I had to make. And if the decision was that they were not in the correct order, then what did I have to do? Do a swap. Okay, so there are really 2 kinds of operations here, and we should probably keep track of both of them and also their total, because that's in some sense a measure as to how much work it took to do this. Okay, so decisions and swaps. And I'll argue that should we count a decision as actually doing something? Yeah, it requires mental effort. Yes? Okay. Or, well, what we're really going to do with this is I'm going to write this algorithm in Python, and I'm going to tell Python to say, do 50 cards and do this sorting method, starting with a random assortment of cards, right? So I'll have it shuffle, and then, all right, it's got its cards, which for the sake of this will just be the numbers 1 through 50, okay? And then I've got, the algorithm programmed, and it's going to go through and do it, and we'll count up the number of steps that it took, okay? Well, if I can make the computer do it once for 50 cards, what could I do instead? I could make it do 50 cards 10,000 times, right? By doing it 10,000 times, what do I get? I'd get a really good average, right? I'd also get, uh, is it guaranteed? Well, so what's the best case that I could get if I had 50 cards in terms of the number of operations? What do you think? Probably 50 or something, right? Because what happens if they just so happen to be sorted already, right? I could get lucky, okay? It's also possible, of course, that I get the exact opposite of lucky, which is, by the way, the exact opposite of lucky for bubble sort is exactly what it was for the sparkle algorithm, okay? Namely that they happen to be sorted, but they're in reverse order, okay? Could happen. Is it likely? Well, maybe not if I have you guys sort it, but if I tell a computer to do it 10,000 times, well, it's more probable that that situation could occur. It's not still not guaranteed, right? Because it could end up that all 10,000 trials are identical. Now that's not likely to happen, but it could, right? In the same way that, the ceiling could burst open and $100 bills could just start raining from the skies. Is that likely to happen? No. Okay. So we'll do this then with the computer and then kind of analyze by looking at our code, if you will, why it is that this bubble sort algorithm is also sort of an n squared thing. Okay. And what does it mean to be an n squared thing? So the last thing I want to leave you with is a mathematical definition, and we'll start with some of this on Friday, is to say this. So a function f of n is called big O of g of n means that for any n there's some constant so that I'm sorry guys, I need to switch to the iPad. Okay, function f of n is called O of g of n means that for there's a constant so that g of n is always bigger than f of n. Okay, now how many of you guys are in calculus? Yeah, did some limit stuff. I could also state this in terms of limits. Okay, and essentially what I want to know is for large values of n, that's sort of the business of algorithm analysis, what's true about f of n? How does it grow with time? F of n could be some really nasty formula, but g of n, I want to find a simpler formula so that one of these inequality holds. And as it will turn out, our formula for g of n for bubble sort and sparkle search or sort, whichever you want to call it, is n squared. So the complexity in some way grows not with the number of cards, but with the square on the number of cards. Okay. And then we'll look at, okay, what about other algorithms and what about things that have nothing to do with searching and sorting, to give you, like I said, sort of a taste as to what algorithm analysis is about. Now, we're basically spending, a week, maybe slightly longer on this idea of algorithm stuff. Future CS majors, guess what? There's an entire full semester class devoted to this very topic. Okay. So it's a huge area in computer science, and I'm just giving you guys the tiniest of amuse-bouches for it. Okay? And if you don't know what an amuse-bouche is, look it up. Okay, the other thing that I wanted to hit before Chicken Tender-a-thon is Friday. What are we doing? Yes, your fun and exciting exam. And how and when will you do it? At 8 o'clock, there will be a folder with exams outside my office. And at 1600 on Friday, what will I expect to see? A fully, them all turned in. Now, those of you who are on the football team, you guys are leaving early, right? You're not leaving early from class. We're not making that mistake again, are we? Glare. But also, guess what you get to do? You guys have to do it before class because otherwise you won't have time to eat before you go on the football game. So plan accordingly. Yes? All right. So when you get the exam, go find a quiet place to work. Put your phone on silent. Right. Give yourself about an hour. It probably won't take you quite that long, but yeah. And you won't need any calculators or anything like that. Some scratch paper maybe, but that's all you should need. All right. See you guys later.